So the next theorem that we have is every constant function is Riemann integrable. So to prove every constant function is Riemann integrable, we'll just make use of a constant function. That is, I'm just taking let f of x equals to k, which is a constant function, on the interval is a comma b, that is a closed interval. And then we'll just define a partition p equals to, that is x1, x0, so on up to xn equals to b, be a partition of a comma b. Now I will define an arc subinterval, IR is equals to xr minus 1 comma xr with the length of that subinterval. And we already know that every constant function is bounded, right? Then from this we can tell f is bounded on each IR. The f is bounded. That is this f, whichever function is there, this is bounded on each and every IR. That is I1, I2, and so on. So now I'm just assuming MR, and we know that small mr and capital MR, what are these infimums and supremums? So these are infimums and supremums of the function f. So as what is f of x? F of x is a constant. So let small mr is equals to k and capital MR is also equals to k. As we are defining it on the function f, what is function f? Function f is f of x is equals to k. So that is the reason we have defined MR and MR like this. Now what we have to take is what is Riemann integral? When 0 is less than or equals to UPF minus LPF is less than or equals to is strictly less than epsilon. So this is a condition for Riemann integral. So I'm just making use of this one. That is, if UPF minus LPF is equals to, what is UPF definition? Summation r equals to 1 to n capital MR into delta r minus summation r equals to 1 to n small mr into delta r. These are from the definitions of UPF and LPF. So as delta r is common over here, I'll just take delta r common. So summation r equals to 1 to n small mr or capital MR minus small mr into delta r. Okay, but what is this? This is equals to some 0, which is strictly less than epsilon. So as 0 is the function, we can tell that f belongs to some r over a comma b. Okay, I'm just taking this mr minus mr as 0. So this 0 will be strictly less than epsilon and f belongs to r over a comma b. Now let us look into another theorem. The theorem statement is this. The theorem number is 10. So what it says is, if f belongs to open interval a comma b, then they are asking to prove that mod f also belongs to open interval a comma b. So to prove this, what is that first we have to take? Obviously the given function. What is that they have given? Proof of the theorem. What is that they gave? They have given that f belongs to a comma b, closed interval a comma b. This is what they gave. This is what we have to prove. So to prove this, we have to make use of what we have to make use of. We have to make use of the definition. So what is that? For all epsilon greater than 0, there exists or such that what is Riemann integrals? UPF minus LPF. UPF minus LPF is strictly less than epsilon. Let this be 1. Okay. Now continuing the proof, and now we have to define partition. So let P is equals to A is equals to x0, x1, so on up to xn is equals to B. So this is partition P. B partition. Where are we talking about? We are talking about the closed interval. So partition on closed interval a comma b. Now till here it is finished. But what is that we have to do? We have to find the ith subinterval. So IR is equals to XR minus 1 comma XR. Okay. And what is delta R? We got to define delta R. Delta R is the length of the subinterval. Is the length of the subinterval. Okay. I hope I'm clear to that. Now continuing the proof. First, what is that we have did? We have just defined the function. We have wrote the partition. We have wrote subinterval, and then we have done with length of the subinterval. Now, since as we have got all this, what will F be? F is bounded on each IR. It is bounded on each IR. Okay. Then mod F will also be. Then mod F is also bounded. As F is bounded, mod F is also bounded on each IR. Okay. If F is bounded, mod F will also be bounded on each IR. Now we have to talk about supremums and infimums. So let us look into that. Small mr and capital MR let small mr and capital MR be infimum and supremum on F. That is the function which is bounded. Okay. On F, of F on IR. That is, we are defining it on IR. Right? Now, as we are defining with MR, we have to even know the derivative of it. So, MR dash and capital MR dash, same thing, be infimum and supremum on mod F on IR. Okay, I think I'm clear to this. Next, now, what is that we have to do? What is that we have to find is this capital MR dash minus small mr dash is strictly less than or equals to capital MR minus small mr. Okay, this is by the definition. Why are we writing like this? Because earlier I think we have studied about something like mod f of f dash of mod f of alpha minus mod of f beta, which is less than or equals to mod f of alpha minus f of beta. Something with mod conditions will be writing the next step. Okay, let us move into the next slide. So MR dash and MR dash. So from that mod condition, what is that? We have a condition that is mod f of alpha minus mod f of beta is strictly less than or equals to mod f of alpha minus f of beta. There's a condition, there is a mod condition. So from this, we can define this as U p comma mod alpha minus L p comma mod f. Sorry, that is not alpha, that is f. Since from 1. What is 1? We have took 1 as UPF minus LPF. Okay? From that, I'm just taking this mod. So what is UPF? Summation R equals to 1 to N MR dash minus M into delta R. This is the definition. Into delta R minus summation R equals to 1 to N small mr dash into delta R. So what is that? You will get summation R equals to 1 to N. Take delta R common. So mr dash minus mr dash into delta R. So but what is mr dash and mr dash from 2? We have written mr dash minus mr dash is strictly less than or equals to less than or equals to mr minus mr. So we can write this in place of this. So this is less than or equals to summation mr minus mr into delta R. So what is this will be? You can write this directly. That is summation mr delta R minus summation small mr into delta R where R equals to 1 to N. This is less than or equals to. This is less than or equals to UPF minus LPF. Right? Obviously, we have studied from one of the theorem telling 0 is less than or equals to UPF minus LPF is strictly less than epsilon. So as this is UPF minus LPF, obviously this will be less than epsilon. right? Since we can tell that, what is that we have took? We have took mod f. UPF minus UP mod f minus LP mod f is less than or equals to UPF minus LPF. So we can tell that this mod f also belongs to R over A comma B. That is what is that we have proved. We just proved if f belongs to R over A comma B, then we have proved this mod f also belongs to R over A comma B. Okay. And what about the converse? What will be the converse? If mod f belongs to R over A comma B, will f belongs to R over A comma B? Do you think the converse is correct? We'll just see with one of the example. Before that, we'll just write the statement. What will that be? If mod f belongs to R over A comma B, then f need not belongs to R over A comma B. For this, I wanted to give you an example. That is, if f is mapping from A comma B to R, such that I'm defining f of x in such a way that -1 if x is less than 0 and 1 if x is greater than or equals to 0 on A comma B. Okay, I'm just defining this f. So what will mod f be? What will mod f be? Mod f of x is equals to obviously 1. See, now mod -1 is 1 and mod 1 is also 1. So mod will be equals to 1. That is okay. Now see, for all x belongs to A comma B. See, mod f of x is equals to 1. But what is f? F has two values. One is -1 and one is +1. So what is mod f? Mod f is a constant function because 1 is constant. It is a constant function. And mod f, I'm just writing it like this. Mod f belongs to k of A comma B. Okay. But f is not Riemann integral on AB because of the following reasons. Why is f not Riemann integral? It is not Riemann integral. Why? There are few reasons. One is a partition, and then you'll have we have to prove this one by using some properties. That is, I just wanted to take a partition, that is A equals to x naught, x1, so on up to xn equals to B is a partition on closed interval A comma B. Okay, this is a partition on closed interval A comma B, and IR is equals to XR minus 1 comma XR, and then delta R is the length on it, length on the R subinterval. And then what is small mr and capital MR? They are infimums and supremums of F on IR. So just remember this example. F of x is not from -1 if x is less than 0 and 1 for x is greater than or equals to 0. We are just proving that f is not Riemann integral. Why is it not Riemann integral? We'll just see. Okay. So I'm just assuming what is small mr. Small mr equals to -1 from that f of x, and capital MR is the supremum, that is equals to 1. So what will UPF be? That is upper Riemann sum. This is equals to summation R equals to 1 to n capital MR into delta R. Delta R is the length. So what is this? MR is 1. So summation R equals to 1 to n delta R. What is delta R? B minus A. B minus A. Okay, remember till here. Now I wanted to define L, that is lower Riemann sum. What is lower Riemann sum? Summation R equals to 1 to n small mr, right? Small mr into delta R. What is small mr? Minus. I'm just taking minus out and then I'm writing summation R equals to 1 to n delta R. So what will that be? Minus of B minus A. Okay, am I clear till here? Now we will be defining integrals. So integral of A to B bar. I hope this is, you remember this upper Riemann sum or upper Riemann integral. So integral A to B bar f of x dx. We'll be defining this. So how will you tell what is integral A to B bar f of x dx? Upper Riemann. Upper Riemann integral. What is the definition of this? Infimum of UPS, right? Infimum of UPS where P is a partition over the set of all partitions. Okay? I think I'm clear with the definition. We have already done with all these definitions. So infimum of what is UPF? UPF is D minus A. So infimum of D minus A. What is infimum of D minus A? D minus A. And in the same way, you got to define this one. What is that? Lower integral, lower Riemann integral. So a bar to b f of x dx. What is that? This is equal to supremum. Supremum of all LPF such that P belongs to phi of a comma b. Right? So what is supremum of this thing? Supremum of what is LPF? LPF is minus d of minus of d minus a. Minus of d minus a. So this is equal to, what will that be? Same thing, minus of d minus a. Right? So do you think integral a to b bar f of x is equal to integral a bar to b f of x dx? What is this? This is d minus a. This is minus of d minus a. Are they equal? No, they are not equal. For a function to be Riemann integrable, what is that you have to have? Integral a to b bar f of x dx should be equal to integral a bar to b f of x dx. If these integrals are equal, you can clearly tell that this is Riemann integral. This is not equal to Riemann. These both integrals are not equal. So you can clearly tell that this f is not Riemann integral. So what is that we have proved? Mod f is Riemann. Mod f belongs to R of a comma b, but f does not belong to R over a comma b. So from here we can tell that it is not, like converse is not true. Next you have few important note points. Just make a note of it. Note. So what is that they are telling is if f is bounded on a comma b. They just gave if f is bounded on the closed interval a comma b. That is, it has both supremums and infimums, or lower bounds or upper bounds. So the first condition is integral a to b bar f of x dx is equals to, as we are talking about the upper Riemann integral, this will be limit n tends to infinity UPF. Okay? And the second note point, like the second bit is same, lower Riemann integral. That is a bar to b f of x dx is equals to limit n tends to infinity LPF. So this is a note point of it. So in this case, the general partition is given by, so as we are talking about the infinities of UPF and infinity, like limit n tends to infinity LPF. So in this case, what happens is the partition P is defined as, generally how is the partition that will define? A equals to x naught, x1, so on up to xn minus 1, xn is equals to b. So this is the partition that will define. But now how will we define is P equals to a plus h, a plus 2h, and so on up to a plus nh. Okay, this is how we'll be defining the partition in this, whenever you have this case, like when limit n tends to infinity UPF and LPF. So where what is h? A already you know the first term. What is h? H will be b minus a by n. Okay, this is what h is. So remember, whenever you have some conditions like this, you got to define the partition in such a way that you get a plus h, a plus 2h, and so on. Now let us quickly look into the problems of Riemann integrals. How are you actually going to solve the problems? So the first problem is prove that f of x is equals to x square. Whether it is a Riemann integral on 0 comma a and integral 0 to a f of x dx is equals to a cube by 3. So this is a very important problem. You will definitely get it for short or either for long. You can expect either in first bit or in the second bit. So make sure that you concentrate on this problem. It will be a bit lengthy but very easy one, only if you know the formula. So what is that we have to take for the given information? So solution, what is that they gave? They've given that f of x is equals to x square. Okay. And what is h? H is equals to b minus a by n. So this is a, this is b. What is b? A minus what is a? 0 by n. So what is h? H is equals to a by n. Okay, remember this one. H is equals to a by n. Now moving on to the partition p. P is equals to what is partition actually? A is equals to x0, x1, x2 and so on. So in place of these, but what is that we have seen in the note point? You got to take partition P in such a way that you get a plus h, a plus 2h and so on. So based on this, we will be defining this partition. So what is that? You'll have 0, a by n, 2a by n and so on up to n minus 1 into a by n to a by n, and then you'll be having n a by n. So n gets cancelled, you'll have a. So this is a partition. Okay, this is the partition that we got. Now what is that we got to find? We have to find infimums and supremums. So I'm just writing mr and capital Mr are infimums and supremums of f on IR, that is the interval IR. So what is capital MR? Capital MR is equals to RA by n whole square. What is capital M actually? The supremum, right? What is supremum in this partition? RA by n whole square. And what will infimum be? Small mr. This is equals to R minus 1 into a by n whole square. Okay, so this is mr, that you have to put it in this form, like as this is x square, you got to put ra by n whole square and r minus a by n whole square. Why are we writing r and r minus 1? Because we are defining it with respect to rth subinterval. Okay, with respect, we are defining it with respective to r. So for that you got to write n into a as it is, n a by n. So as we are defining with respective to rth subinterval, you have to write ra by n whole square is supremum, r minus a by n whole square is infimum. Now we have to find UPF and LPF. So what is UPF? Summation r equals to 1 to n capital MR into delta r. So what is this? This is equals to, what is capital MR? Summation r square a square by n square into delta r. What is delta r? The difference. So that will be a by n. A by n is the difference, right? What is the difference of a by n and 2a by n? 1a by n is the difference. So that is what we are writing. So that is equals to, what will this be? A cube by n cube are constants. So take that out, summation r square. So if you define it from r equals to 1 to n, what will that be? A cube by n cube is equals to, a cube by n cube into summation, that is 1 square plus r square, r equals to 1 to n. So you'll be having 1 square plus 2 square, right? 2 square, 2 square plus 3 square plus so on up to n square, because r is equals to from 1 to n. So what is sum of squares? 1 to n sum of squares. So this is n into n plus 1 into 2n plus 1 by 6. Okay. So this is what you got, and take n common from this. If you take this n and this n common, you'll be having n cube. We'll write it a bit clearly. So what is that you got? A cube by n cube into n plus 1 into 2n plus 2 n plus 1 by 6. So I'm just taking n cube common. So you'll have a cube by n cube into, if you take n cube common, what is that you'll have? This is 1. This will be 1 plus 1 by n. This will be 2 plus 1 by n, right? By 6. So this n cube gets cancelled. What is that you'll be having? You'll be having a cube 1 plus 1 by n into 2 plus 1 by n by 6. So now we got to find a 0 to b bar. because actually we have to find a to b bar, but what is the interval that you have? 0 comma a. So 0 to a bar f of x dx. So that is equals to limit n from the node point, limit n tends to infinity UPF. So what is UPF? Limit n tends to infinity a cube into 1 plus 1 by n into 2 plus 1 by n by 6. So if you put n tends to infinity, this will become a cube 1 plus 0 into 2 plus 0 by 6. So this will be equals to 2a cube by 6. So this will be a cube by 3. Right? Till here. This is 1. In the same way, you got to find for LPF and then you got to find the lower Riemann integral. So how will you find that one? Taking LPF. So what is LPF? LPF is equals to summation r equals to 1 to n small mr into delta r. So what is small mr? R minus 1 into a by n whole square. So summation r equals to 1 to n r minus 1 whole square into a square by n square into a by n. What delta r is the difference. So take all a's and n's out. What you'll have? A cube by n cube. A cube by n cube. So this is equal. This will be into r equals to 1 to n. What is that you have? R minus 1 whole square. Right? So what is r minus 1 whole square? If you put r equals to 1, r equals to 2 and so on, what will you have? A cube by n cube into, you'll be having n minus 1 into n into 2n minus 1 plus 1 by 6. Right? So what is that you'll have? A cube, take out all the n's common. So you'll be having n cube into 1 minus 1 by n into 2 minus 1 by n by 6. So these n cubes will be cancelled. What is that you'll have? A cube into 1 minus 1 by n into 2 minus 1 by n by 6. Now you got to apply integration for this. So how will you apply the integration? That is for lower Riemanns. So integral 0 bar to a f of x dx. So this is equals to limit n tends to infinity LPF. What is that you got? LPF? Limit n tends to infinity a cube into 1 minus 1 by n into 2 minus 1 by n by 6. So in the same way as previous, you will get 2a cube by 6. So this will be equals to a cube by 3. This is second one. So what is first and second? They both are equal. Hence, what is that you can write from 1 and 2? We can write that integral 0 to a bar f of x dx is equals to integral 0 bar to a f of x dx, that is equals to a cube by 3. So we can conclude that if f belongs to r over a 0 comma a and integral 0 to a f of x dx will be equals to a cube by 3. Hence solved. This is what we have to prove and this is what we have proved. I'll just give you one homework problem. Just try it by yourself and let me know whether what did you get. Prove that f of x is equals to 2x plus 1 is Riemann integrable on 0 comma 2. Just prove this and tell whether is that a Riemann integrable and what is the value of integral, what is the value of the integral.